Good afternoon. It's my great pleasure to welcome Professor Jianwei Miao from UCLA to present a COSI seminar today. John did his PhD in physics at Stony Brook, where he did a beautiful experiment showing the first demonstration of coherent diffractive microscopy using X-rays. And at Stony Brook, in parallel, he also did a master's in computer science and biomedical engineering. And he did his undergraduate work in Hangzhou University in China. And he is now professor in the Department of Physics and Astronomy and member of the California NanoSystems Institute at UCLA. John has many awards, including Outstanding Teacher of the Year in the Physics Department at UCLA in 2006, a Sloan Foundation Fellow, the Werner Meyer-Isle Memorial Award, and he is a guest scientist at Icon in Japan. And so I'd like to welcome John to present our COSI seminar today.
First of all, I want to thank Margaret and Henry and also Ario for inviting me to be here. And it's the second time to Boulder, and actually I also brought the sunshine from California. So I'm going to talk about the technique that I have been working on for more than 10 years. Actually, I started when I was a graduate student. And it's a coherent diffraction microscopy and the application in nanoscience and biology. So I'm especially interested in coming back to Boulder because I have a long-term collaborator. Margaret and Henry have collaborated for a few years and have been very productive. And I'm going to show some of the results that we work together. So the convention, I hope everyone knows the conventional microscopy. Most of microscopy based on lenses, right? The lens just do a Fourier transform, right? And now there's another way to do Fourier transform. If I shine a laser, right, on the object, like a laser shine on my watch, you get that speckle pattern. That speckle pattern is nothing but a Fourier transform of the surface of my watch. If you shine this side, the speckle pattern is different, and you can see the definite difference, right? Because the surface structure is different. Okay, which means there's a one-to-one correspondence. These structures, the Fourier transform, get the other one, you only get the magnitude, that get the other pattern. The question is whether from this pattern you can uniquely get a structure back. So whether from this pattern, right, you can determine the surface structure of my watch. And this is both sides. So that's just the inverse problem. Now, this is a famous, we have to solve the so-called phase problem. We only measure magnitude, but not the phase information, right? So the idea is very simple. You just have an X-rays electron laser shine an object, and you get a coherent diffraction pattern, solve the phase problem. The technique okay, let me just show the important phase information. That's done by my student Sela Saha, and that just did last year before the election. So, and everybody knows this man and also this man. So she did a Fourier transform this one, okay? So get a magnitude of phase, and Fourier transform this one get a magnitude of phase. So combine the magnitude of Obama with the phase of McCain, the inverse Fourier transform, and the magnitude of McCain with the phase of Obama, the inverse Fourier transform. And here this one looks like a B because the phase information from B, and this one looks like A because phase information from A. So at least for our eyes more sensitive to phase information. But unfortunately, we only measure the magnitude. The phase information is lost. So the question, how can we get the phase information back? Now historically, this has been a subject that people been very interested in on this subject for a long time. I mean, a few Nobel Prize awards related to the phase problem, like Dirac methods, crystallography, so another method. And for solving protein crystallography, they have isosurface replacement of them. And also in mathematicians are interested in this method as well. For example, Mark Keck, in 1966, he wrote an article published in American Mathematical Monthly. So the title is "Can one hear the shape of a drum?" So you have the drum of the different frequency. Okay, you have the frequency, the vibration of the frequency. From that, just look at it. We don't watch. Can you just from the frequency, if you know the frequency of the vibration of the drum, can you get the shape? Can you deduce the shape of the drum? Okay. Now it turns out that there is a Herman Weyl. Actually, he's very top mathematician, also a physicist. He also kind of interested in this problem much earlier. And now they found that for many shapes, one cannot hear the shape of the drum completely. It's not, but for some convex shapes, with analytic boundary, the answer is yes. But for our problem, we're actually more difficult than this one. We not only want to know the shape, but we also want the internal structure. Because if you want to study biological structures, or for example, cell, or some nanostructures, you not only want to show the surface, but also internal structures, right? So the problem actually a little more difficult. And now also, we are dealing with, the previous one showed just purely from a mathematical point of view, which means you just want to, from the magnitude, how to solve the phase problem, how to get the phase information back from the magnitude. Just do the Fourier function, the Fourier transform, you throw out the phase information, how to get a phase back. That's mathematical phase. But for physical phase problem, actually a little more complicated. I'm going to show you one of the famous experiment by Tonomura, the Japanese very famous scientist. He did the famous double slit experiments using electron. And his electron, he did electron one at a time. I'm going to show his experiment because I think it's very interesting. And actually, he did it one at a time, so you can see one electron at a time. And there should be some sound, but anyway. But you can see, so electron at the beginning is just random. So if you look at 100 electrons, you shine 100 times, the pattern will be completely different. So if you 100 electrons, there's no phase. Phase doesn't make sense, right? Now later you will see when only the number of the electrons getting larger, get a statistic effect. Then you will see some interference effect. And that interference effect, we call it coherent diffraction, or the speckle diffraction. That can help us find the phase information. So the phase information, I mean, I just want to use this experiment to illustrate the phase problem, physical phase problem, actually is even more difficult than mathematical phase problem because the statistical effect. You have larger number, then you get interference. But if 100 photons doesn't make sense. 100 photons, you should one at 100 photons, another 100 photons. The pattern is completely different, right? So one photon doesn't have the phase information. Right? And his famous experiment shown that actual photon interference with itself, not with the neighboring photons. So that's actually predicted by Paul Dirac. So that's a famous experiment because he's shown that photons really interfere with itself. Okay, so I'm going to talk about a technique called oversampling method to solve the phase problem. Now, this is just a brief early history of the oversampling method. And David Sayer first, in a very short, like half-page paper, he kind of no equation, just have intuition. He thinks that if you measure the intensity at the black peaks, but also between the black peaks, then may be able to get the phase information. I'm going to explain in detail later, okay? And then FinUp developed iterative algorithm for phase ratio of diffraction intensity. But he didn't understand at what condition the phase can be. So what's the reason why phase is reconstructible? Now, then based 1982, and partially based on kind of Sayers paper, that he claimed that in order to phase can be retrieved from diffraction intensity if the intensity is oversampled twice, at least twice in each dimension, means you measure it at the black peaks, but also between the black peaks. Okay. The reason is because I think many of you are familiar with Fourier transform, Fourier theory. With any object, you get the Fourier transform, or you get a diffraction pattern. If you do inverse Fourier transform diffraction pattern, you get an autocorrelation function. The size of autocorrelation function is twice larger, as large as the object itself. So in order to, that's based on his argument. But in 1998, now at that time I was a graduate student. I joined started that project in 1996. So we shown that actually basic criterion is overly restricted. So we proposed a different explanation. We use the number of the equations and the number of unknown variables. So we don't need, actually based on our criteria, we don't need oversampling twice in each dimension. And so far, at least all the experiment results is consistent with our theoretical explanation. And then this is 1999 we did the experiment, and now it's become quite a big field, especially and the coherent source like Henry and Margaret are developing, and also this national big large scale facility actually free electron laser. Now it's become a very hot area. So I'm going to tell you about what's the oversampling method. Now to understand oversampling, let's first take a look at Shannon sampling theorem. Now Shannon was engineered at Bell Lab The Bell Lab really made an impact, big impact to the society. And this year's Physics Nobel Prize, and CCD actually also was first invented at Bell Lab. And Shannon was engineered at Bell Lab in the 1940s. So he was thinking, at that time, he's considered as the father and the founder of information communication theory. So that especially nowadays, everybody uses this digital, and we call it digital era. I think actually contributed to him. And at that time, he was thinking, assume there's a signal confined within A, he wants to send the signal from one place to another place. People from other places can receive the digital signal. Now the analog signal can be done, but how to receive the exact digital signal? He was thinking that problem. I mean, really way ahead of time. Now, of course, electron engineering can do Fourier transform and get this wave, right? So then he asked, how to sample these points? Of course, if we send digital signal, the fewer the better. But in order to get exactly, if you send just one point, of course, you cannot recover this back. So he's shown that actually, if this A, you sample 1 over A, then you can exactly get this back. It sounds like a magic, but actually it's not. It's just in physics, it's like a Heisenberg uncertain relationship. Exactly, it corresponds to Heisenberg uncertain relationship. And this frequency called Nyquist interval. Actually, Nyquist published a paper before Shannon. Now, if you compare of course, if you phase, then you can get it sampling 1 over A, you can get it. But if you don't have the phase, Fourier transform, you only measure these intensity points, and you cannot get Fourier. You cannot do inverse Fourier transform. Cannot this back. Cannot get it because you have to solve the phase problem, right? And mathematically, we can show that if you sampled at 1 over A, this intensity cannot uniquely determine the signal. You can get infinite number of signals. I mean, one way to demonstrate any phase set multiplied by this magnitude to inverse Fourier transform, you get a signal. Is that correspond, right? So which means it's not a unique intensity, not uniquely determine this one, and this uniquely determine this intensity, but this not uniquely determine. It's not uniquely determine other way around, because the reason is because the phase information is lost. Now, but if we do oversampling, you sample finer than this. So you measure like this intensity, right? You measure the intensity finer enough. It's finer enough, it's measure more intensity points. And it turns out if you measure more intensity points, mathematically that's the way uniquely determine the signal. So there's a one-to-one correspondence, which means the red curve, the red dot plus the black dot uniquely determine this one. The red dot plus the blue dot, or the black dot plus the blue dot uniquely determine this one. Now in this paper, actually, that's we explain. We introduce this equation: lambda is a wavelength, A is a sample size, delta P is a pixel size. Like I think Henry has already initiated this experiment. You're gonna try this experiment this week. So delta P is the pixel size, X the distance from the sample to the detector, and capital O is oversampling ratio, linear oversampling ratio. This has to be larger than 1. So we shown in the 2D this has to be as long as larger than square root of 2. Should be unique, which means number of the measured point, independent point more than unknown variables. So that's kind of the basic. And now experimentally, how do do the oversampling? How do we do the oversampling method? Let's assume you have a particle or a biological sample size n by n. If you measure diffraction pattern, because it's continuous, it's because it's not a crystal, so the diffraction pattern is continuous. If you use the CCD, the CCD sample at 1 over n, that's called a Nyquist interval, right? In order to get this back, you have to inverse fast Fourier transform. But if you do the same experiment, same setup, but you make the distance a little larger than this case, or twice larger in this case. So each pixel here, each intensity points here corresponds to 4 points here. But the spatial resolution is the same. You don't get an extra intensity point. You don't get extra information about the object because the diffraction angle, the angle relative to the detector is the same. So if you know this phase information, you can use inverse fast Fourier transform to get an object. This n by n is also n by n. But you notice if you can get the correct phase information, mathematically we can show this region must be zeros. So one way to show it, we can use zero density region to help us to find this. Now here I want to emphasize this is like a pretty mathematics. If you oversampling larger than larger, this is zero larger than larger. But it's not So you may say, if I make oversample, this is the trade-off. First of all, this coherence of the beams is related to the oversampling degree. If you large oversampling O, which means increase this distance, this has to be better, and this angle has to be smaller. And also the signal each pixel signal noise ratio is lower. So it's a trade-off. What's the best optimal oversample ratio for the experiment, right? And then I assume I already convinced you that if you oversample diffraction pattern, there's unique phase information encoded inside diffraction intensity. But the next question, how to reconstruct it? So we use the iterative algorithm and modify original developed by Gertzberg, Saxton, and Finup. And we have recent version. I think it's a little better than previous one. So we started on the computer. We generate a random phase angle. We don't need any model. It's model free. And combined with measured data, and we get this Fourier transform. And the inverse Fourier transform, we get electron density. And we modify the electron density because we know that some region must be zeros. And inside object should be positive. And we call it physical constraint. The physical constraint is very, very important. Now, I can give you some example. People like super resolution or super resolution. Super resolution, they also use applied information. Which means if you want to measure, for example, position of, they can get a few nanometer, some professor here, they can measure a few nanometer resolution position, for example, a bead. The reason is because they know exactly the geometry of the bead. And then they just get a scattering the peak, the Gaussian, the shape of the bead, to find the center. You can get even 1 nanometer resolution, right? And the reason is because the bead is exactly know the bead. It's applied information. So this is called a physical constraint. I mean, same as here. So a lot of the structure, even biological samples. Biological samples, the cell is not just random like atoms. They have a lot of structures. This is why, for example, in protein crystallography, protein crystallography always use all the constraints. They use, for example, atomicity. Atomicity means all the atoms have some distribution, and molecular replacement means a lot of proteins structure actually they have some in common. And they use many constraints, histogram matching and positivity. So this is kind of another way that all the physical constraints can be, because some information already known, right? It's just you cannot go the other way. And then get a new electron density, apply faster Fourier transform, get a Fourier transform. And every time you update the phase information, you always use measured data and update the phase information. Yes?
So is there a way, if you don't know the size of your constraint exactly, and if you make that constraint bigger, let's say, than the actual object, you tend to see the reconstruction get poorer. Is there a way to detect or some secondary method that would allow you to know when that's a very good point. So how do you uniquely determine the support? We call the support, the boundary of the object. And we always, because in our reconstruction, first of all, from a speckle size, the size of a speckle, you can roughly estimate the object, size of object. And we always use we call loose support, the support larger than object. And then for the reconstruction progress, you can update your support. So you can begin.
You can begin, many algorithms actually develop, but slowly can find the support, can update the support. Okay. Yeah. And here shows kind of experiment demonstration that the SEM image of test sample, and this actually uses X-ray, soft X-rays, X-ray diffraction pattern. Now, one thing I found is because many of them are students, I just want to share my personal view. If you want to try some challenging experiment, and it's always at the beginning, it's always been tough because people. When I tried this experiment, this project was not funded, and people just don't think this will go anywhere. And so it's kind of it was hard, very hard. But that's dependent on personnel. I kind of like. If I succeed, I'll be big. If I failed, I'm probably go somewhere else. I'm not staying in academia. At that time, I was thinking Wall Street. Because 1990s, it's very difficult to find a faculty position in physics. I mean, the economy is bad, and that was physics, especially very bad. Not so many openings. A lot of physics students. Some of my friends actually graduated before me. They went to Wall Street and earned like 100K at that time. So I thought I want to take some challenge projects. That's kind of just a gamble, some gambling kind of mentality. But eventually, it paid off. So it's kind of so you have to think big. I think you have to think big. There's many projects. You can get a succeed. Okay, follow that path. You can get a PhD. But if you want to really do something that kind of really big, you have to come from nowhere. So which means you have to take a risk. There's no free lunch, right? It's like a Heisenberg uncertain relationship, like investing in Wall Street. If you want to get a big rewarding, how can you? I mean, you have to take a risk. Otherwise, how can you get a big reward? And so here I'm going to show the reconstruction of the always we start with random phase angle, and then outside we push close to 0, and inside with positivity constraints. And after a few hundred iterations, we reconstructed this object. Right? And another thing I found is that if I want to do something completely new, always the society were against it. I mean, most of it against it. Actually, we have another paper that I collaborate with Henry, and a lot of people against me. I get used to it. I think it's right no matter what I was there. I mean, this is very important. If your idea is a little new, then people accept it easily. But if we're ahead, if you look at any new idea, if we're ahead, it's always people against you because it doesn't make sense to them. It makes sense. If it makes sense to them, then they will figure it out, right? This idea is difficult there. This why I believe that's kind of the way. I don't know if it's right or not, but at least that's personal. That's my personal view. Okay, so I just put the same scale. Then you can see the very good the example very well. Now, you notice the contrast very well. The reason contrast very well, I thought about it, the reason is because conventional microscope, you have the DC term, which means the electron beam overlap with the scattering wave. The scattering wave is many orders smaller than the electron wave. It's one use lens. So it's just like a ripple in a wave, ocean wave. It's very difficult to tell, only the ripples. Now, there's one very beautiful method to overcome it, which is fluorescence microscopy. Fluorescence microscopy completely removes the DC term, completely removes the ocean wave. So you can see very small ripples. Like in daytime, you can see the stars. I mean, at night you can see the stars nicely, but at daytime you cannot see it because sunlight is completely dominated the wave. I mean, that's exactly corresponds related to the lens-based microscopy. So one way is use different wavelengths, filter it out. So fluorescence, this is why it becomes so powerful. Now our method doesn't use the different wavelength, but use a special angle because our dielectric beam is block. Dielectric beam is block. We call it beams. It's much smaller than the diffracted beam. Our diffracted beam covers the whole CCD chip, but dielectric beam is just a few pixels. So the signal, the dielectric beam is here actually, few pixels. The signal is all from the sample, so there's no DC term. I think this is very important. This is why the contrast, there's no background. It's so clean. These are all people asking so clean because there's no background, and the DC term is. So here I want to show the 3D reconstruction. I want to show some applications. Yes.
What was the wavelength in that picture?
So the wavelength with 17 angstrom. It's 1.7 nanometer soft X-rays. And here it shows gallium nitride quantum dots nanoparticle. Now another thing very important, especially some students want to try experiment, the missing center we found, it took us a long time. If you look at this diffraction pattern, actually we have a low resolution optical microscope image, calculate diffraction, magnitude filtration, few in here. The reason is the dielectric beam intensity much stronger than the high resolution diffraction pattern. Many orders, from here to here is many orders scale intensity variation, right? And so the measurement is kind of challenging, but of course the advantage is you don't need the lens, you get very high contrast. And so the beam missing data, turns out we find it's very important, and in this paper we've shown if the missing center was confined within the central speckle, and then always guarantee reconstruction. The reason is that the central speckle corresponds the integral of the total electron density. So that doesn't change the structure, only changes the DC corresponds to the total electron density. And we show the different angles, and from many angles we can do the 3D reconstruction. And here shows isosurface rendering of the structure. I'm going to show the movie. And overall, this size is about 800 nanometers, and at least 300 nanometers. You can see that these many kind of platelet structures, and it's very consistent with SEM. Now, advantages of this technique, because we use X-rays, we can see the internal structures. And this, I think we believe the first time revealing 3D gallium nitride, gallium oxide core shell structures. And the different electron density correspond different colors. You can see the each slice corresponds 17 nanometers. So you can see it's really like a nanotomography. This core and the shell structures, you can see really 3D. And recently we also tried, we call it resonant X-ray diffraction microscopy. And this is silicon samples with doped with bismuth. And we just want to demonstrate, take a diffraction pattern above the bismuth edge and a bismuth M5 edge and below the M5 edge. But the silicon contrast is almost same because the two energy silicon contrast are very similar. And then we take two diffraction patterns. We can reconstruct the distribution of the bismuth. And here shows one is this is above the bismuth M5 edge, and it's the 2.5 about 6 keV. This is 2.55 keV. You can see the overall speckle size. Speckles look very similar, but if you plot it, you can see some difference. One is below, one's above. There's some variations, and because we think the bismuth distribution. And here shows a reconstruction. This is a reconstruction. This above the edge. This above the edge, and this below edge. And now we did an independent reconstruction. These two curves correspond independent reconstruction along this center line, and this is very consistent. And then we align them together. We have to normalize and do subtraction, and this shows a subtraction distribution of the bismuth. And this is much larger than the reconstruction error. Reconstruction error is about very small. It's about 1 to 2%, but here it's we have a very high intensity, high density doping. So you can see on average it's about 10%. And this is SCM image. You can see it's very structure overall consistent with our reconstruction image. But of course, our X-ray can see the internal structures, not only internal 3D internal structures, but also see elemental specific images. Now, another project we collaborating with a group at Harvard. We want to study bone samples. Now, bone is a very interesting structure. When I dig into it, I find it's very. For example, for a newborn baby, the bone is very flexible. On getting older, for older people, the bone is getting very, very brittle, right? Because easier to break. And there's a kind of biological reasons because the children, they always keep falling down, so the bone has to be very flexible. But getting older, they walk slowly, and the reason is because you want to protect all the organs. All the organs getting older, they cannot keep falling down. So this is kind of that's kind of one way to do interpolation that's related. But from molecular level, we try to understand what's the kind of the structure of the bone at a molecular level. What causes the structure change? And there was a model proposed by Hodge and his student in 1960, Petruska in 1963. That's called a Hodge model. And so if a bone, if you get a cross section and you can make it the marrows inside, and each one called osteons. If you zoom in, actually this is made of collagen fibers. Each fiber is made of collagen fibers. I mean, it's amazing that nature made these hierarchical structures. And each fiber, if you zoom in, actually this is based on Hodge model, made of collagen molecules, very soft molecules. About 300 nanometer in length. And these are not like continuous. You have actually some hole. So this one between this one is a hole. And this distance from here to here is based on their model 67 nanometers. And now the bone is not only support our body, but also the main reservoir for the calcium and phosphorus. And the calcium is very important for biological process. More than 99% of calcium is installed in the bone, right? And so that's kind of the model. And we studied the bone X-ray diffraction imaging of a fish bone, herring fish bone, at different stages. So young fish bone, and this shows the low mineralization, which means young age. And you can see we get our resolution is about 20 nanometers, and between 15 to 20 nanometers, we can see, if we zoom in this region, you can see this actually H1 collagen fibrous. You can see there's some region dark spot, and this about 67 nanometers. And we believe that's actually related a lot of concentration of the calcium, the nanocrystals. And now, if we rotate this at different angles, actually this kind of disappeared. So it's not it's not. So this is not always like a one orientation. It seems like there's the orientation inside the fiber is kind of it's not always in same direction. It depends on which direction you look at it. And then we look at the highly mineralized bone samples. These two are highly mineralized bone samples, and you can see if you look at zoom in this region, actually this one we think is collagen fibrous, and it become dark. It's we think it's a complete filled in with these nanocrystals, and same as this we call it the band structures. Actually, if you fill in, they actually form the band structure based on the Hodge model. So based on this, actually, we did a lot of studies. We did a low mineralization, no mineral bone, low mineralized bone, medium mineralized bone, highly mineralized bone. We proposed a model, and so at the beginning, this like a new bone, there's kind of almost no nanocrystals, and this is why for children need a lot of calcium, because they need to form these crystals to make their bone become stronger, and then this kind of a crystal started growing in this region, and this body fluid is glowing, and the crystal, people measure the crystal actually the size. It's about 30 by 30 by typically by 2 to 5, 30 by 30 by 2 nanometers, 2 to 5, very thin. So the C-axis, so the crystal, the long axis along this direction, and then they grow more and more. Eventually they fill up all the holes, and we think they hold the region between the collagen, the space between the collagen molecules. And then actually in this, if you look at it, it feels to call it the band structures. Now, this work is people use the electron TEM, high resolution TEM also study this, but our advantage is we can use this without any kind of a sample preparation, much easier. X-ray, much easier sample preparation, so it's more close to the native status. So the sample is sent to us in the vacuum pipe, the vacuum tube, and when we do experiment, we just open the sample and put it in our chamber. We get diffraction pattern. It's very close to the natural the environment. Unlike TEM, TEM have samples very, very thin, and they have to do a lot of tedious work. So that's kind of and recently we tried coherent axis diffraction image of a biological sample, yeast spore. Now we choose yeast spore as relative radiation hard, so can withstand it, because we haven't tried to try with a fixed sample and want to see a 3D reconstruction. So we get many 2D diffraction patterns. We do each reconstruction, and then get a 3D reconstruction of the. And here shows a 3D reconstruction, and you can see the surface is very bumpy. And this SEM image, not the same one, but similar. You can see the kind of consistency. And for a lot of us, yeast spore actually it's very bumpy. Yeast spore is like if at yeast at low nutrition, each yeast form like a fishing yeast form 4 spores. This spore is very tough. If you put it in the desert, after a few days, they can still survive. And if you give them environment, each spore become a yeast. So that's actually the same. And here we noticed there actually there's something stick out, and we found this actually is the spore germination. We cut it through this one. You can see there's some high density region inside of this. There's something stick out, and importantly, we can get internal structure. So we can really get we label all the different organelles. And I'm just going to show the movie. This is the movie. I'm going to show the rotation of the movie. What's not showed? Okay, and you can see the origin. This one is the nucleus, and this ER, and this vacuole. And there's a lot of organelle. Of course, there's a lot of complicated structures. We cannot label them all, but you can see the mitochondria. We can see. So really can see a lot of information for biological sample, internal structures. Okay, and also, now one of the justification for, at the beginning I mentioned X-ray free electron laser. This U.S. is building it, Stanford is building it, Berkeley wants to build one, and all the other countries want to build. One of the main justifications is to use, hopefully to use coherent lensless imaging to imaging single molecules. Now, so we tried this experiment at synchrotron. We tried what's the for synchrotron, what's the resolution we can get with a single virus. So we try virus. This is herpes virus, and it's about 200 nanometers. And we put on a silicon nitrogen membrane, and this pinhole X-ray coming. And it's a very difficult experiment because this pinhole is 20 microns. So it's typical the diameter of your hair. You have to align the diameter of your hair to a 200 nanometer. Everything in the dark, complete, it's in a box. And we found actually we figured out a way how to do it, and we get diffraction pattern. The signal is very 8 hours exposure. I mean, it's just a very weak signal because even TEM is difficult to see the value. They have those negative stain. Nowadays it's cry EM, but the contrast is very, very weak. That's the problem because for biological samples the contrast is very, very weak. Now, fortunately for our technique, as I said, because our DC term is not included, so everything is from the signal. So there's no DC term. So the contrast of the technique is quite good. And here shows the contrast with high contrast. And this is our reconstruction. This is SEM image of same sample, and this is negative stained TEM. Negative stained, they use high Z element, and this is high Z element actually image at high. And this is a diffraction pattern, and we can, from the density evaluation, we can quantify actually this. We believe this capsid, each virus has a membrane and a capsid. This capsid that inject inside the cell. So the membrane attached to the cell, and then fuse with the cell and inject the capsid. And this actually AF image shows the height of the similar herpes virus. And now I'm going to talk about actually the project that collaborating with Margaret and Henry. I felt very fortunate that we started this project, and we first actually did experiments, lensless diffraction imaging with a high harmonic source. Actually, at that time, Richard Sandberg, who graduated and now is a postdoc at Livermore, and we did it together. I used a high harmonic generation source, and this is a beautiful technique, high HHG source. Two world experts are sitting here, so I'm not going to talk about the principle of this. But this is a nice paper. It's a review paper on the high harmonic generation and applications, especially not only just for imaging, but also for attosecond science. There's a lot of applications. So here, just our setup. We have a laser coming in, and this noble gas just generate this nonlinear effect, right? Generated this high harmonic soft X EUV source, and this aluminum just removed the high orders, and this Miller just gave focus to a small spot and also removed some other high orders, and then put a sample here called diffraction pattern, and the lambda, the wavelength we use 29 nanometers, and lambda over delta lambda is 200, and here shows the first demonstration experiment. We have a mesh put on a pinhole, and this diffraction pattern. And from this diffraction pattern, we reconstruct and we do line scan, and the resolution about 200 nanometers. And now we can do much better, but this is just first demonstration experiment. And recently, in the French group, they did a single shot experiment, and Margaret and I even wrote a news article for Nature on that. And we also collaborate with Margaret and Henry and Richard. We collaborate with Jorge Loga from Colorado State, and we did a UV laser source, and we can get actual resolution much better. We can almost do 1.5 lambda resolution, 71 nanometers. So personally, I feel although like a large scale synchrotron source or next generation synchrotron, like a NSF, Brook Evans built this NSLS too, $700 million. These large, kind of have a big potential, but tabletop, I think it's very important because tabletop, especially for biological applications, biologists really want their tools, their instrument inside their lab. Because it's very easy. If you want to check study the biological samples, you can put it in, get a sample. And they want to do a systematic studies, not just to get one image. They want to get 100, 1,000 images, then they can get some information. Biological samples are very different from the material samples. You have to do many. There's no for biological cells, that no two cells are identical. So I hope that I talked to some of students and Margaret and Henry students, and they're developing this tabletop soft X-ray lasers. I'm very hopeful. Hopefully, we'll come back and probably next year we get some good results from that. And finally, I'm going to just talk about also that it can be applied for electron device. So you may ask why for electron? The electron can get very high resolution. Right now, you can get 1 angstrom resolution. The advantage is because the diffraction is a more efficient method. If you just study biological, this actually is studied by somebody else, is from this paper, actually shown bacterial rhodopsin 2D crystals. You get a diffraction pattern versus image. If you plot them in the same scale, logarithm scale, you will find at a high resolution, the diffraction gives you more information. The lens is good, but at the high resolution, the lens there's always problem. And not as they improve the lens, of course, but still diffraction pattern is, if you can get a perfect good reconstruction, I mean get all the reconstruction, the diffraction still give you most information, right? And so like in 2002, we did some simulation, and we numerical simulation and a nanocrystal, and we can get with signal noise ratio equal to 3, we can still reconstruct this one slice, single slice of the. We can still get the reconstruction, and then we tried to do some experiment, but somehow one group at Illinois, they did the first experiment, carbon nanotube. Now, if you put a carbon nanotube in TEM, you will not see. You only see 4 lines, because of the contrast is not so many atoms here. You cannot see that, but because diffraction, you only get, as I said, the DC term is not there, so you can see more high. You can see some structures, and you can see the helicity. The helicity is important because that determines whether it's a semiconductor, insulator, or conductor. You can determine the helicity. Okay, finally, I just want to come a discussion the lens-based with lensless imaging. And there's a very famous book by called The Art of War by actually the philosopher in China about 500 BC. And I think he's really right. He said the best strategy to win a war is to have no war. And in Napoleon and Mao Zedong, he has a very good military, in terms of military, is very good. And Douglas MacArthur, they claim they have drawn inspiration from the work. And a few months ago, there UCLA, there's Jackson died in a UCLA hospital, and well, everyone knows because overdosing, right? It's just you too much this medicine, and based on his theory, just the best medicine is no medicine. That's true. If you do exercise, you don't need a medicine. The healthiest person, the longest person, they don't take medicines. They just eat a little food and healthy food and do some exercise. They are healthiest. If you take a medicine, this medicine is really so from his book you can really the best medicine is have no medicine. That really makes sense. This is why I try to say the best lens is to have no lens. Now, fortunately, I hope I'm not offending somebody in this audience because you use lens, but no, of course, but different. But what do you want to do? If you want to purely get a high contrast image and good information, so if you can get the simplest setup, I think that can get most of the information. I'm not saying that we. It's like what do you want to do? If you want to go from here to, I think when I give a talk in one place, one audience asks. So in that case, then people, why you develop the lens-based microscopy? I told them it's dependent on what do you want to do. So for example, if you want to go from here to Los Angeles, you have to fly. So airplane is better choice. But if you want to go from here to Denver, you better drive. You don't fly; it's not efficient. So it really depends on what you want to do. I think it's, in some cases, if you want to get a purely high quality 3D image, high contrast lenses, this lensless image is a better choice. But if you want this really depends on what you want. So here's a summary. I hope that I convince you. Oversampling diffraction intensity gives the phase information, and there's historically the phase problem because people are dealing with crystals, and crystals they only get the intensity at the black peaks, right? And it turns out that oversampling really gives the phase. And we did an experiment demonstration in lensless diffractive imaging, and we also tried a resonant X-ray diffraction microscopy for element-specific imaging of buried structures. and 3D structure studies of materials and biological samples. And we're also collaborating with Henry and Margaret. We demonstrate lensless diffraction imaging using a tabletop high harmonic generation source. And we proposed electron diffraction microscopy, and this was done by other group. And the application we think is very broad. It's really nanoscience, material science, and biology, especially with future coherent X-ray sources. So I think the imaging overall, I think is a really good field to be in. Now it's a really good time to be in. And finally, I want to thank all my collaborators. I have some wonderful collaborators, including Margaret and Henry and Richard. And here's my group at UCLA, and all the other. I thank all the other collaborators. Okay, thank you for your time. If any questions.
Thank you so much, John, for a wonderful talk and for a lot of advice for us as well.
Not for you, definitely, but for the first students.
That was very interesting. So, are there any other questions?
I think I'm missing the key point. You're not getting any phase information from oversampling. You're using phase retrieval, right?
Yeah.
That's how you're getting the.
What kind of phase information is because oversampling diffraction pattern, then in principle, there's one to call it there's a unique phase, existing unique phase of the unique phase information.
Okay, so that's my key question.
Yeah.
There's a difficulty with convergence proofs of most of these phase retrieval.
Mm-hmm.
So does oversampling change the ability to have a convergence proof? Do you have an existence in convergence proof for phase retrieval with oversampling?
Well, we have a convergence, but now mathematically we have for the convergence, of course, without noise we have showed, but with noise mathematically very difficult to prove. Without noise we can show it. It's unique. We can show the algorithm.
Because of oversampling? I mean, I thought phase retrieval works.
Without noise, with noise, of course, mathematically we cannot prove because noise is very difficult to be taken into the model. But all this, so far, the field developed to a point that as long as get a good diffraction pattern with noise diffraction pattern, the reconstruction always very straightforward. Reconstruction, if we get a good diffraction pattern, and so I always emphasize when we do experiment, always is good quality, high quality pattern, which means you want to reduce get a high signal noise ratio as high as possible and reduce some background, and then the reconstruction is very straightforward. We have no problem. So far, I mean, it's not just many groups, probably in this field, maybe 30 groups worldwide working in this area. Reconstruction, the problem is more or less kind of, it's already in the pocket. I would say that. And now it's get a quality diffraction pattern. With noise almost, of course, depends on how much noise. If the noise dominated the signal, then of course, why don't you expect? But with reasonable signal noise ratio, and even with very weak, like we tried wireless, you can reconstruct it.
But does oversampling change the story?
Yeah, oversampling changes the story because it makes it unique. Otherwise, it's not unique. Otherwise, if it's not unique, they will not converge, which means you don't have a unique solution. Oversampling just you measure more intensity points, then you just make it the convergence. That's unique solution. Now, of course, when the noise is there, the unique solution become. It's not just one solution. It could be a few solutions. So we sometimes average. We do independent reconstruction and average it. So which means it's not a solution at one point because it could be near that point. There could be a few kind of a convergence to a few different points, but they're very close to that point when there's noise. So we usually do many averaging. We do reconstruction, independent reconstruction, and then average. But they're very close. They look very close. With the comparison, they look very close.
But in either case, with noise, you have convergence proofs.
With noise, as I said, with noise it's difficult because the noise is very difficult to take into account. Without noise, we have the convergence proof. But with noise, we just use numerical simulation. We use experiment data. It's all. I mean, if a reasonable noise, signal noise ratio, we can reconstruct it.
Kind of a continuation question.
Yeah.
So what factor of oversampling are you talking about? I mean, when you say oversampling,
Yeah.
I assume you mean you're sampling above a Nyquist rate, but what are you?
Well, so typically in our case, we use oversampling a little larger than 2-inch dimension. So for experiment, because it's trade-off. If you're oversampling too small, then the number of the measured points, especially with noise, you want to measure the points, independent points, a few times larger than the unknown variables. Or if you oversample too large, then the signal noise ratio on each pixel would be smaller. So it's a trade-off. We find that the oversampling ratio, overall oversampling ratio for 2D or 3D object, between around 5, larger than 4, it's a little larger than 4, it's optimal. Most of the group actually in that range, a little larger than 4 overall when there's noise. Yeah.
Without noise, you still require oversampling though for your conversion.
Without the noise, we still need oversampling. Without oversampling, you cannot. There's no unique solution. You cannot reconstruct.
Okay, but what factor of oversampling do you require for your proof, though?
Without a noise, oversampling ratio just need to be total oversampling ratio need to be larger than 2. So which means each dimension you need a sampling finer than square root of 2, finer than the Nyquist interval for 2D object. A cubic root of 2 for 3D object, that's enough. Just need that's exact correspond 2 correspond number of equations equals the number of unknown variables. If it's more than larger than 2, then measure the independent points larger than unknown variables, then in principle can reconstruct.
Yeah. How much harmful stress for a living cell or biological sample?
Well, so for biological samples, the main difficulty is the radiation damage. That's kind of a problem. As a matter of fact, we applied the iterative algorithm to for CAT scan, also CAT scan. This is not related to your question, but I'm going to answer your question. The CAT scan, the CAT scans really every year in the U.S. 65 million examinations per year, and this is $1 million project. Around $5 million every year. They sold like more than 1,000 CT scanners. Each one's over $1 million. So it's a $1 billion project. CT account for only 15% of the total medical imaging. If you take up a radiography of this, but account for about 70% of the total radiation. It's the largest man-made radiation source. So more than a nuclear power plant. That's CT. I mean, it sounds scary, but it's useful. Can I diagnose the cancer or the detection? Now we recently applied the iterative algorithm to use a physical constraint. We can reduce radiation. With the experiment data, we showed at least more than 50%. So this is why actually some of the physicians at UCLA, they're excited that so that's kind of related. Come back to your question. For biological samples, the radiation damage is a major issue. And so there are 2 ways to kind of try to reduce radiation damage. One is freeze the sample at the liquid nitrogen temperature. And that actually we're going to pursue that direction. Just cool the temperature, maintain the very low temperature, then can actually reduce the radiation damage a lot. And the second method, and people still try, is actually use very short pulses. Very short pulses, we hopefully can get a diffraction pattern before the sample is destroyed. Now, there's some numerical modeling or some preliminary experiment to show that that's maybe the case. So if the pulse is short enough, a few femtoseconds, then you can capture diffraction pattern before the sample is destroyed. So there's 2 ways. Seems like the first way can reduce radiation dose, can study biological cells, but the second method probably to the single molecule imaging is short pulse.
Okay, well, if there's no other questions, then let's thank John again
Okay.
for your time.